Solarsilicon, creating carbon-free energy independence. Our solution is to combine disruptive metallurgical technology and concentrated solar power to produce green solar silicon for low-cost PV solar panels. Our objective is to create large-scale market-wide adoption of renewable energy within the next 5 years. The solar power reaching the Earth meets the world's total electric power demand 10,000 times over. Our industrial process captures some of this sunlight using parabolic trough concentrating collectors. The reflected light in the form of solar heat is used to heat up molten salt using Solarsilicon advanced proprietary thermal receiver technology. Rather than heating up a conventional metal pipe, high-optic transparent quartz pipe is used to transfer the light, heating the molten salt directly, substantially reducing the radiation losses and improving the thermal efficiency of the receiver. Heating molten salt directly to produce solar silicon is a key innovation that eliminates the 60% thermal to electric energy conversion loss experienced with traditional solar silicon industrial processes. Moreover, the proprietary electrochemical oxygen extraction process produces silicon and titanium amongst other metals for less than 25% of the energy needed in conventional processes. To begin, metal silicon dioxide is extracted from the ground in the form of quartz, crushed and pressed into a preform. The next step is, the preform is introduced to a reduction vessel filled with heated molten salt provided by the concentrated solar collectors. The molten salt used is calcium chloride. It's the same salt that is spread on our icy roads during the winter. Even though the molten salt is not regarded as a pollutant, the salt is recycled. The temperature is held between 800 and 1000 degrees Celsius, and that contrasts with many conventional processes that need to melt silicon in excess of 2000 degrees Celsius before refining can take place. The lower temperatures and the shorter processing times that the ECO-X process requires obviously means considerably reduced energy requirements. The whole vessel is kept in an argon-rich atmosphere to avoid reoxidizing the silicon. The pellets form the cathode or negative electrode and a reduction vessel. When an electric current is passed between this cathode and a positive carbon anode, the oxygen is removed from the silicon oxide. The oxygen passes through the salt in the vessel and reacts with the carbon anode to form only small amounts of carbon dioxide that is bubbled off, collected, compressed and broken down, leaving only the pure metal on the cathode. The next step is to remove the reduced or pure metal, but because the oxygen atoms have been extracted, it is in a sponge form. This step involves crushing the sponge into a powder and then washing out any remaining impurities. Then once the silicon has been dried, it's ready to be used. Using the example of titanium, the complexity of the ECO-X process over that of the complexity of Kroll is clear to see. With about 3 volts of electricity used for the electrochemical process at elevated temperatures, the bulk of the energy exiting the ECO-X process is recycled and kept in a thermal energy storage unit. With molten salt giving up less than 1% of its energy over 24 hours in a well-insulated tank, the excess energy after running the ECO-X process is generated to produce electricity at times where demand is highest to help recover capital and plant operating costs. Since the steam is generated from higher processing temperatures, the steam cycle is maintained at optimum efficiency, minimizing conversion losses. The resulting system produces utility-grade power for the grid and an industrial process to help make the solar panels for decentralized photovoltaic systems, avoiding line losses and producing energy where you use it, whether in your home or business, for true carbon-free, affordable energy independence.